Hello everyone, and welcome to this webinar on improving your software team's productivity and efficiency with fast virtual prototypes. Here's the agenda we will be following. First, we'll take a look at the challenges facing software development teams today and how virtual prototypes can help with these. We'll follow that with a short demo to introduce you to virtual prototypes and their role in software development. Next, we'll look at some methodologies for boosting the performance of virtual prototypes, followed by a demo showing some of these in more detail. Next, we'll examine how virtual prototypes provide a very efficient platform for software debug activities and include some capabilities that are unique to that methodology. We'll follow that with a short demo of these capabilities. Finally, we'll take a look at the role of virtual prototypes in continuous integration and regression setups, followed by a short demo illustrating this. Okay, so let's get started with the first topic, which is how can virtual prototypes help with software development? The first point to make here is that software is becoming the dominant component in many products, with automobiles being a prime example. At the same time, software is becoming ever more complex, with aspects like multi-core and virtualization becoming the norm. This means that the software development activity is now the critical path in many product developments, and for that reason, the productivity of software development teams is a key determinant of when products can be brought to market. The obvious conclusion from this is the need to ensure that software teams are as effective and efficient as possible. These teams are often geographically distributed, and even if they are co-located, they are likely to be working remotely today. To address this, many novel software development methodologies have been developed. Many companies have adopted virtual prototypes as a way of shifting left their product development, that is, starting development sooner. Many new development strategies such as Agile, DevOps, and of course continuous integration and continuous deployment have also been introduced to address this problem. But to make an impact, virtual prototypes must be both fast and efficient for software debug and also integrate well with the latest development techniques like continuous integration. The main advantages of using virtual prototypes are first of all their availability. Since they're not dependent on the availability of RTL designs, they can be created and deployed much earlier in the product development cycle ahead of the availability of hardware. But not only does that allow teams to get started early, since they are pure software, they are also much easier to distribute to remote teams. In addition, since virtual prototypes are created with a modelling style that abstracts many of the hardware details that software is not aware of, like detailed bus timings, they can provide speeds of execution close to that achievable on the target hardware. But these advantages would count for little without the efficient debugging experience that virtual prototypes provide. It's possible to run exactly the same software on virtual prototypes that runs on the final target hardware, eliminating the requirement for a porting activity when hardware becomes available. A further major advantage of virtual hardware is the observability and controllability that it affords. Both hardware and software events can be observed easily, and this makes the diagnosis of issues, especially those at the software-hardware interface, much easier. Virtual prototypes will also work with existing third-party tools like debuggers, which means that there is no additional investment required in the acquisition of and training for new tool chains. They can also provide links to real-world environment, such as the ability to connect to a real Ethernet network or to use real USB devices. As we have already seen, simulation performance is key to making virtual prototypes useful tools, and here we will discuss some of the aspects of this. The most important component of any virtual prototype is the instruction set simulator, or ISS, which is executing the target code. For software development purposes, this is generally designed to be instruction accurate only, with architectural details like pipelining or bus timing abstracted away. As we mentioned before, a key attribute of virtual prototypes is that they should execute your target software without modification, and so the design of an instruction accurate ISS focuses on doing this as efficiently as possible. In many cases, device virtualization can be used to improve simulation performance. This is now a well-known technique with much support in standard OSs, and it can also be employed in virtual prototypes, where a register-accurate model is not required for the software development task being tackled. Areas such as graphical performance can be greatly improved using this technique. This also is the advantage of making virtual prototypes easier to create by saving the effort of modelling these features accurately. Another technique which can be employed in virtual prototypes is checkpoint restore, allowing the state of a simulation, both in hardware and software, to be saved and then restored at a later time. We will discuss this in more detail soon. The Synopsys Virtualizer Studio tool provides an extensive set of features to enable this efficient environment for the software engineer to debug his code. As previously mentioned, integration with popular debugging tools such as Louterback T32 is available, and there's also a native integration with the popular GDB debugger. It also has a native debug capability which is called VDK Debugger, and this provides unique hardware and software code debug features. This allows monitoring of hardware activity inside the VDK as well as software activity and the ability to view and analyse these together correlated in time. There's also extensive scripting support which is very useful for doing things like error and fault injection. Another key aspect is the ability to connect the simulation to real-world interfaces through virtual and real-world I/O. For example, virtual prototypes can connect to a physical Ethernet network or control physical USB devices connected to the host system. It is also capable of being employed in hybrid emulation and prototyping scenarios with Synopsys HAPS and ZeBu products. Okay, so time for a short demo, which will start to show some of the features we have been talking about in action. In this demo, we will show how Virtualizer Studio provides a productive and efficient environment for software development by allowing you to run embedded Linux software stacks with excellent performance and create, build and debug your Linux applications all from within the Virtualizer Studio IDE. So first let's take a look at the virtual prototype, or VDK, that we're going to use for this demo. Here is the Eclipse-based main IDE of Virtualizer Studio, and we can also see here a virtual LCD panel which we can use to display graphical content. In the design browser of the Virtualizer Studio IDE, we can see the various components that make up our VDK. We have a CPU subsystem containing 2 clusters of 4 ARM CPUs along with interrupt controller support. And if we look in the perifs block, we can see that we have some memory, a few UARTs, an Ethernet controller and a USB subsystem. If we take a look in the USB subsystem, we can see a USB 3 controller and a model of a USB mass storage device. The mass storage device can be configured with a file system image which allows the embedded software running on the VDK to access the files on it just as if it was a real device. We shall see that in action later. Now if I select one of the devices in this dialog, like the USB 3 controller, you can see that the left hand side of the panel is populated with information. These are the registers and signals of the model, and we can see the values of these in detail. This is a good example of how virtual prototypes allow you to see many more details of the activity in your system. Of course, virtual prototypes are not only about the hardware, but also the unmodified target software stacks that we want to run and debug on them. Here we can see the set of software images that we can run in this particular VDK. We have Android 10 and 11 images, as well as a couple of Linux images built using Buildroot. The VDK allows you to select different configurations to swap seamlessly between the images, and these are selected here. I've selected a Linux configuration and started up the virtual prototype. You can see here that Linux boots very quickly in a matter of seconds. And once we've reached the login prompt, we can log in and we're ready to start some testing. Now the first thing I want to do is use the USB 3 cockpit shown here to plug in our virtual device. You can now see this new device being detected by Linux and assign the designation SDA. Now to make our new device available to Linux, we need to mount it using the mount command. In this case, we will use the location /mount/USB. When the device is mounted, we can go to that location and we can list the files on our USB device. Now I have a few short movies in here on the device, and now we can play these in our virtual LCD. Now to do this, I'm going to start up an X Windows session and use the MPV utility, which is installed in the Linux file system. So we can start up the MPV utility and point it to one of the movies on the USB device. The application reads the file on the USB device and starts to play the movie, as you can see, with very good performance. We can also run the GLX Gears demo app for OpenGL. As you can see, this also runs with very good performance on our virtual prototype. Now, if you notice, we also have a small application on the USB stick which is designed to open JPEGs using the frame buffer device in Linux. I'll end my X session and run this utility and see the results. So as you can see, the JPEG which we've selected has been opened on the LCD device. Now, the sources and makefile for creating the JPEG to FB application have been imported into Virtualizer Studio, and this now shows up as an Eclipse project in the project browser. We can now edit, build and debug this application all from within Virtualizer Studio. So for now, let's just make some edits to the program. And here I'm just going to change some logging messages. Okay, so I will save those changes, and now we can rebuild a new version of the program in the Virtualizer Studio GUI. So I just need to select the program and ask it to build. So the application is now building and will complete soon. And hopefully without errors. So the application is built on our host machine using an ARM cross-compiler. Now I'm using the VP9D model in the platform to allow me to mount the location of the project executable in the file system of the embedded Linux running on the virtual prototype. You can see this location specified as a parameter of the VP9D model. This allows us to instantly deploy and run the updated version of our application on the virtual prototype. Now we can check out the updates we made by debugging the updated application using GDB and GDB server. We can connect GDB to our platform by using the Ethernet model that we saw earlier. This model features real-world I/O, which allows it to connect to external applications and networks. Again, this can be done directly in the Virtualizer Studio IDE. First, we start our application with GDB server. Then we start our debugger configuration. The GDB debugger connects to the GDB server application running on the VDK, and we can start to debug our application. At this point, we transition to the debug perspective of Virtualizer Studio, and when we are there, we can start our application executing. In the debug configuration, I've set a breakpoint at the start of the main routine of our application, and so the debugger stops there. At this point, we can use the debugger stepover function to navigate to the function that does most of the application's work. And when we get to that function, we can step into it. Now in this function, we can see that one of the activities that this function does is to process the arguments that were passed to the program. And you can see these visible in the variable view. So if we continue debugging, we eventually get to the routine that actually does the display of the JPEG on the LCD display. And if we jump over that, you can see that the JPEG has now been shown on the LCD display. Finally, we can just step through our program and run it until it terminates. Okay, so now let's take a closer look at some of the technologies that can be used to boost the simulation performance of virtual prototypes. Synopsys Virtualizer Studio now features a set of models based on the industry standard Virtual I/O specification. These can be used in virtual prototypes in situations where register-accurate models are not required, and provide a much more efficient and simpler way to simulate many types of I/O. For example, the Virtual block model can be used to access file system images which are present in the host machine's file system. This effectively makes these available to the simulation as if they existed on devices attached to the simulated hardware. We will see an example of this usage in the next demo session. The Virtual Input model can be used to implement human interface devices like keyboard and mouse. Along with a virtual LCD device, this can be used to implement a touchscreen using a keyboard and mouse of the host system. Using this methodology means that we can avoid having register-accurate keyboard and mouse controller models in our virtual prototype, thus saving the effort of developing these. The VirtIO GPU model allows us to boost the graphical performance of virtual prototypes by offloading OpenGL commands from applications to the host machine's GPU. This gives a very significant boost to performance when running a graphics-intensive OS like Android or a graphics-intensive application. It can be used in situations where you don't need a register-accurate GPU to carry out your development. Virtual hardware also allows you to employ techniques like checkpoint restore to speed up testing even more. With checkpoint restore, you can save the entire state of your simulation at a point of interest and then use that checkpoint to get quickly back to that state. Having created your checkpoint, you can now use it across all of your testing resources, for example, to skip past long initialization phases. This can vastly increase the amount of testing that you can do in a testing cycle. This feature can also be used to help diagnose failures. For example, it could be used to save the condition of the system under test at the point of failure, meaning that this point can be reached quickly for further diagnosis. It can also be used to take regular snapshots of the system state during long test cycles. These states can then be used post-testing to accurately locate the point of failure, as well as to get quickly back to the state of the system just before the failure occurred. Okay, let's now see a demo which will show some of these techniques in action. Let's first take a look at the virtual models we have in our virtual prototype and describe what we are using them for. Now we have 4 virtual block devices. These are used to access file system images that are present in the host's file system. If we look at the parameters for these devices, we can see that they allow us to make the Android image files available to the simulation. This abstracts away the need to implement an actual hard disk drive controller and drives in the simulation, making it easier to implement and much more efficient to run. Also, the software drivers required to implement this functionality are much simpler, as it doesn't have to deal with the complexities of a real device. The next set of virtual devices implement touchscreen capability using the host mouse and keyboard. Again, these devices very much simplify the design of the virtual prototype, since we don't need to have models of actual keyboard and mouse controllers in our system. Finally, the Virtual GPU model serves the same purpose, but for graphics performance. This device allows us to offload graphics operations to the host machine, greatly improving the graphics performance of our software stack. This is of great benefit when your virtual prototype is running a graphically intensive application or a graphically intensive OS like Android. We can see the effect of this in our virtual prototype when running Android and applications that run on top of that OS. So now I'll select the Android 11 configuration and start up the simulation. Now for brevity, I've speeded up the video here, but the entire Android boot with all graphics operations that entails takes around 5 minutes to complete. We can observe the progress of the Android boot on the virtual LCD panel and see the various stages until the familiar Android homepage appears with the application icons. Once we are booted, we can start up our installed applications like Angry Birds. Again, I've speeded up this process to save time. However, once the game has been started, you can see that the graphical performance is such that it allows smooth interaction with this graphics intensive application. So now I can select the game I want to play and select the level and start my selection loading. When this is complete, I can actually start to play the game. Once the game has completed its initialization, I can use the host machine mouse to simulate touchscreen operation and interact with the game just as you would on a normal phone or tablet screen. But we do not always want to go through that startup phase when we are debugging our applications. The checkpoint restore feature in Synopsys virtual prototypes allows us to get straight to a point of interest quickly. If I now pause the simulation at some interesting point in the game to which I want to return, I can start the process of creating a checkpoint for that, which I can subsequently use anytime I want to get back to that point. Now I give the checkpoint a meaningful name which I can use when I want to restore it. Here I've simply called it Angry Birds. So Virtualizer Studio is now saving the entire hardware and software context of the simulation, including connections to external processes like the LCD device in this case. Now I can restart the virtual prototype and carry on playing the game from the point at which the checkpoint was created. Everything works just as it did before the checkpoint was created, and I can continue to play the game and carry out my testing activities. Now, when I want to start a new testing session, I can simply find the checkpoint I created earlier and restore it. So Virtualizer Studio is now recovering the state of the simulation when we created the checkpoint. When this process is completed, we are back at the point where the checkpoint was saved. Now I can simply start the simulation from that point, and as before, everything works as normal. I can continue my testing session without having to go through the process of booting the OS and starting up my application. Again, since we have an Ethernet model in the virtual prototype design, it's possible to connect the usual Android tools to the virtual prototype. So for example, I can connect the Android Debugger Bridge, or ADB, and carry out some operations. So ADB connects to our simulation, and now we can check the devices that ADB is connected to. And if we do that, we see that our virtual prototype is listed there. Next, we can take a look at the Android logcat output, which lists all the activities of the processes and applications in the system. We can also open a shell into the Android console and use this to interact with the simulation just as if we were using the console in the virtual prototype. We can also use the same Ethernet connection to connect Android Studio to the virtual prototype. This allows you to work at the Android application level. Now, this can be useful for creating small test applications to drive end-to-end testing of your software stack and then deploy these on your virtual prototype. Let's move on now to look at how virtual prototypes can provide a very efficient debugging environment for the software developer. Virtualizer Studio provides both controllability and observability of the software and hardware aspects of your system design. Controllability allows you to start and stop both software and hardware aspects of your simulation completely in sync, unlike hardware where clocks and other signals will typically continue when your software is paused. Similarly, you can set breakpoints not only on software events in your system, but also in hardware events such as interrupts. This fine-grained controllability also applies to stopping and starting using an external debugger. Observability means that you can easily see the models that make up your design and even observe and change register values and signal states in the Virtualizer Studio IDE. The analysis capabilities allow you to capture both software and hardware events in your system and plot these graphically in time-ordered graphs. Events are correlated in time, allowing accurate investigation and diagnosis of issues at the hardware-software interface. Virtual prototypes can also provide a vital aspect of the testing environment required for embedded software, and that is links to the real-world environment. They do this through the implementation of real-world and virtual I/O features in the models that make up the virtual prototype. The real-world I/O feature allows such models to connect to real-world interfaces such as PCIe, USB, or Ethernet. For example, it's possible to connect the virtual hardware to a real Ethernet network or to a real USB device. Virtual I/O allows the virtual prototype to appear like a real device to the software OS hosting the simulation. In the example shown, the VDK appears as a PCIe endpoint to the guest OS, running on the VirtualBox being executed on the host PC. These features allow virtual prototypes to interact with the real-world environment, providing the real-world stimulus required in test setups. Many of the models shipped with Virtualizer Studio implement a feature called Fast Track. This feature allows these models to detect issues with how they are being configured or used in the system. For example, if a set of registers are programmed in an order that violates the specification, or if registers are programmed at an inappropriate time, the software developer is warned of this and can take steps to fix the issue. Another usage of Fast Track allows the detailed tracing of model operations. This can be invaluable in detecting and diagnosing situations where host software is not following the correct procedure for model operation. The Fast Track traces can point this out and even indicate the software routine which is behaving incorrectly, allowing the software designer to quickly pinpoint the issue. In the next demo, we will take a closer look at some of these features and how they can be used in a typical software development scenario. One of the most significant values of virtual prototypes in debugging comes with the unique visibility it gives you to the software and hardware operations in your system. Although this is of most value down at the lower layers of the software, it's often the case that effective debug of these lower layer operations requires us to run higher level software to reproduce the exact conditions that the lower level software is expected to handle. This is where end-to-end testing of software stacks comes in, and in these cases it's vital that your test platform can run the full software stack efficiently and accurately. We have already seen that we can exercise the USB controller capability in the platform using a virtual USB mass storage device. We will now show you how you can effectively debug the USB operations that occur when high-level applications are run in Android. We can once again plug in our device and mount it such that it's visible to applications running in Android. To do this, I have enabled some of Virtualizer Studio's software and hardware analysis capabilities. On the software side, we have enabled Context Trace, which will allow us to see the high-level Linux processes that are invoked when our application is running. Function Trace will allow us to see lower-level functions that are running to interact with the USB controller device. We switched these capabilities on for all the cores in the VDK. At the hardware level, we can enable tracing of accesses to the USB controller registers, and we can also trace the TLM2 transactions from the CPU that are interacting with them. We can also trace other activity of the USB controller signals, like interrupts, and here we can switch on value trace for those. Another unique capability you can exploit with virtual prototypes is the ability to see the internal workings of the devices that make up your system, something that's just not possible with hardware. Synopsys models have been implemented with a feature called Fast Track, which allows you to see this detail. It can even warn you when your software is configuring the device in an inappropriate way. This has been enabled both for the USB controller and for the USB mass storage device. Now we can use the browser application in Android to see the files on our virtual USB device. So if I click on the USB dialog here, we see the same files that we saw earlier, some short movies and some pictures. We can now click on one of the JPEGs and choose the viewer application that we want to open it from the browser application. So in this case, we'll choose ES Image Browser, and the picture is now displayed on the virtual LCD screen. We should now have some results from the analysis features we enabled, which will allow us to analyse what was happening in the system as we opened the JPEG. First, let's take a look at context traces we have obtained for each core in the VDK. Now there's a lot of detail here, so let's focus on the traces for just one of the ARM cores in the system and look at that in a little bit more detail. And we'll choose the trace for CPU 0 of cluster 1. So the graph we can see here shows us the time-ordered sequence of process activations. So we can see higher level Android processes and lower level kernel processes, such as the routines that are invoked to do interrupt handling. Now the Details tab below the graph shows us some statistics regarding the most active processes. Here we see that the image loader process and the renderer thread are high on the list, along with the Android display process, as we would expect. If we now look at the function trace results, we can see a similar setup. Now we have for each CPU in the system a detailed time-ordered list of the functions executing on the cores. Again, we'll focus on just one of these to examine the details. On this core, we can see in detail the functions that are being invoked to carry out the USB operations. If I now add the value trace for the USB interrupt signals, we can see how this correlates with the USB functions being executed. This type of hardware and software analysis is unique to virtual prototypes and allows you to see the interactions between the two domains in detail. We can now also add the register trace and TLM traces to get the full picture. This allows us to see the CPU interactions with the USB 3 device in detail and to see the effects of these transactions on the device's registers. Finally, we can look at the fast track traces we've obtained from the USB 3 controller device and the USB storage device. These show a time-ordered sequence of events as recorded by the models in the VDK. I've selected the traces for the USB 3 controller, and the Details tab gives us information about the events handled by the model, along with details of the CPU that initiated the event and even the software routine that carried out the operation. This allows you to easily correlate events in the model with the software processes that initiate them. I can select the USB storage device now, and we see similar information regarding its operation. The messages in the Details tab in this case also give information on how the mass storage device has been configured in the virtual prototype. This information can be invaluable in diagnosing virtual prototype setup issues, especially for complex models with many configuration options. In the final part of our webinar, we will look at how virtual prototypes support today's software development methodologies like continuous integration. So what is continuous integration, or CI? Essentially, it's the practice of merging the work of all developers in a team into a shared mainline codebase several times a day. A key aspect in making such a practice work is automation. Ideally, we need to ensure that after every submission, the codebase builds and all the tests we have execute without failures. This is where a build server application like Jenkins comes into the picture. As well as build and test automation, quality metrics such as code analysis, coverage, and performance can also be measured, giving an overall picture of your product's health. For many users, CI is just a step along the way to what is known as continuous deployment. When a project has reached this stage of maturity in terms of build and test, the product should be in a constant state of being available for release to customers. So how does Virtualizer Studio support a continuous integration environment? The first aspect is that all Virtualizer Studio features are represented by Python APIs, which means that tool operations can be scripted. This allows build and test systems to use scripts to integrate with Virtualizer Studio. Virtualizer Studio also features some specific APIs to support continuous integration. These allow you to develop Python tests which can start up and configure simulations, run some tests, and then cleanly shut down the simulation. This is ideal for supporting integration with build and test environments. Since Virtualizer Studio is an Eclipse-based tool, you can install plugins to support the usage of source code control systems like Git. These features make it possible for virtual prototypes to effectively replace hardware in regression setups. This provides many advantages. Since virtual prototypes are software applications running on standard hardware, they can be deployed more flexibly and more cost effectively than the equivalent hardware. They are also perfectly suited to cloud deployment. Okay, in the final demo, we'll look at an example of a continuous integration environment using Virtualizer Studio, Git, and Jenkins. Let's see how Synopsys virtual prototypes can be easily deployed in a continuous integration environment using Git as the source code control system and Jenkins as a build and test server. Now in this setup we have 4 projects all managed under Virtualizer Studio, and we can see these in Project Explorer. The first project manages the scripts that provide the integration between Jenkins and Virtualizer Studio. The second is the VDK itself, and the third is our software project called Numbers, which simply prints out sequences of numbers of various types. The fourth is the set of tests we have developed for our Numbers application. All of these projects are managed under Git, and in the Git repositories tab we can see our local Git repository and also the central repository to which we will push our updates. On the Jenkins side, we have a project set up to manage the building and testing of our application. Let's look at how that's been configured. So Jenkins is also using Git as a source code control system, and we can see that this has been set up pointing to the same central Git repository as we saw in Virtualizer Studio. In the build trigger section of the configuration, we can see that Jenkins will poll this repository looking for changes, and when these changes are detected, it will kick off a build and test cycle. In the build section, we can see the actions that Jenkins will take on this trigger. It will build our VDK, build our application, and run the tests we have defined for it. It will then produce a test report and a code coverage report. Now if we go back to the project, we can see that our last run has some failures, so we can take a closer look at this. If we open the detailed report for this build cycle, we see that we have one test failure. This is the test that checks our application's capability to print Fibonacci sequences. We can also see that the check-in which triggered this build involved adding this routine to our application, so we have a good idea where to look for the issue. So we can now go back to our development environment and take a look at our application. From our Numbers project, we can open the source code and start to look for the issue. We can locate the Fibonacci routine, and when we do, we can see that there's an obvious error there, so we can easily fix that. We save our changes, and we can see that our change is detected in the Git staging tab of the Git plugin. And so we can stage it here and commit our change to the central repository with a suitable comment. Since Jenkins has been set up to detect changes in this repository, the result of our push operation is to kick off a Jenkins build and test cycle. We can see this happening in the Jenkins GUI. When the build is triggered, Jenkins goes through the process of pulling all the sources from the Git repository into its own workspace and carries out the operations we saw defined earlier to build and test a clean version of our projects. When this is done, it reports the results. Now we can see that our application is passing all its tests once more. Now we can also check out the code coverage our tests are providing for our application, as this capability is built into Virtualizer Studio and the data which it captures is processed and displayed by Jenkins. So we can locate our application here, and we can see the general coverage we're getting in methods, lines, and classes. But we can also go down to the next level and look at the source code for our application and see the lines of code that are actually covered. This type of analysis allows us to easily spot gaps in the coverage indicated here in red. And so we can then develop further tests which actually exercise those lines of code. So that's my last demo, and so I'll move on to a summary of what we've covered in this webinar. So we have seen how virtual prototypes can improve your software productivity by providing fast execution of complex software stacks like Android, allowing end-to-end testing of your software. Device virtualization techniques, which can harness the host computer's resources to make your virtual prototypes even faster, especially improving graphics performance. Checkpoint restore capability to skip long initialization sequences and get quickly to the point of interest. Unique debug capabilities like fast track and hardware tracing that allow you to see both hardware and software events in your system. And finally, integration with third-party tools to create development environments that allow your teams to use the latest development techniques. Okay, so that's the end of the presentation part of this webinar. So now I'd like to move on to Q&A. You can submit a question to me by entering it in the Ask a Question text field and clicking Submit. So if you have any questions on anything you've seen, please do that now. Okay, so I have a first question I'm going to try and answer for you here is a question saying, how many peripherals are supported at a time on Virtualizer Studio? Okay, so, well, the answer to that one is there isn't really a specific limit. Now, we've been creating virtual prototypes for, maybe many years now, and of course, over the years, the complexity has increased and increased, and, we can support now really very complex VDKs with not only lots of peripherals, but actually also lots of cores. And so you can create really very complex systems in Virtualizer Studio. Another aspect is that we also have the capability to hook together simulations. So, if your design naturally partitions that way, you can actually create different simulations and connect those and get them to interwork. So that's another way that you can kind of scale up within Virtualizer Studio and have really pretty complex simulations. Typically, what we find customers do is they will create their virtual prototypes almost as required, so that you would typically just implement a subset of your functionality initially and start doing some software development on that. And then as your software development progresses, you can add more and more peripherals or CPUs or whatever. So there's not. I hope that's a good answer to that question. But yeah, there's not really a limit on what peripherals can be supported. Okay, let me see. I've got another question here. So we showed Virtualizer Studio integration with Jenkins and Git. Are other build and test environments and source code control methods supported? Well, the answer to that one is yes. In fact, the setup that we're showing here is actually just an example of what can be done. So we picked Jenkins and Git really just to illustrate it. So the APIs that Virtualizer Studio has should allow you to create an integration with many different kinds of build servers, etc. The APIs are there. They're really the important thing here. So in the case we showed, we used some scripts, some shell scripts, which evoked the Python calls, API calls, and ran the tests. So that can be adapted to whatever build system you want to use. Also in the source code control, we used Perforce. We used Git there, but you can also use Perforce or Subversion or other source code control systems. That's really a function of the plugins that are available for Virtualizer Studio. Okay, yeah, I have another question here. So can Virtualizer connect to other simulators for co-simulation scenarios? Yes, it certainly can. So, you can connect to other simulators, things like MATLAB you can connect to. You can also do co-simulation with emulators and and other kinds of simulators as well. So yeah, there's a lot of connectivity that you can do with Virtualizer. And again, this is part of the whole idea of creating simulations that might consist of multiple different simulations, but also connecting kind of to the external environment as well. So we have a capability called VSI, which allows you to basically do that kind of thing. Okay, I have another question. Does Virtualizer support XIL API? I'm not sure about that actually. That's a question that I'll look up for you and get back by email if that's okay. Okay, another question here, what are the different input formats? So ELF, hex, FMU. I guess these are sort of different things here. So, if you're actually loading images into Virtualizer, so that the images of your software that's going to run, yes, that will tend to be in ELF format or hex format, and yes, we can support those. So that's typically what you would do. You would create an ELF file of your firmware that you want to run, and that can be loaded in actually a few ways. It can be loaded directly into a device, or it can be loaded via the CPU. So those things are supported. I also see FMU. So yes, that's also supported. So you can have FMU connections. Okay. So yeah, if you've got any more questions, yeah, please submit them, and I'll do my best to answer them. So another one I have here, is it possible to use third-party debuggers with Virtualizer Studio? So yes, we support a few different third-party debuggers. So in the demo you saw, we have GDB, so you can connect GDB, but we also support connection of Louterback, Trace32, ARM Design Studio, Green Hills Multi. These are all supported for ARM CPUs. Okay, any more questions? Okay, yeah, I've got another one here. So what types of virtual and real-world I/O are supported by Synopsys models? So again, I guess in the demo, we showed kind of two things. We showed USB. So we had the USB controller in the simulation actually connected to another virtual model of a USB device. But that controller will also support connecting to a real USB device, which you would plug into the computer hosting the simulation. And that's kind of what we call real-world I/O. So we can connect to actual real devices using USB 3. But we also support USB virtual I/O, and in that case, your VDK would be the USB device, and that can appear like a real device that's plugged into the host machine. So that, for example, allows you to do things like if you have applications running on the host machine, then they can connect to and control the device that's being simulated. We also support real-world I/O for PCIe as well. So where a PCIe device can be plugged into your host machine, and that can be enumerated and controlled by the VDK running on the machine. So we also have another range of I/O options we have are like serial. So for UARTs, it's possible to connect to real serial ports and virtual serial ports and things like that. Okay, yeah, I've got another question here. So does Virtualizer support the latest Neoverse cores from ARM? Yep, so absolutely. We support all the latest ARM cores. So we have a relationship with ARM, and we integrate the absolute latest and greatest ARM cores and models into Virtualizer on a very regular basis. So, you know, every time we release a new release of Virtualizer, it will tend to come with the latest ARM models and the latest versions of those ARM models actually as well. Okay, another question here. Can Virtualizer connect with DSpace, Alexico, hardware in the loop systems? Again, I'm not sure about that question. Let me get back to you on that one via email, if that's okay. Okay, any more questions? Okay, so if there are no more questions then, it just remains for me to say thanks very much for attending. Thanks very much for your attention, and goodbye.